Is this thing on? All right. So this is Practice Makes Perfect, Extreme Cassandra Optimization. I originally had a more boring title for this talk, and before I came to DataStax, they gave me this title for it. I kind of like it now. There's a bit of a discrepancy on the slides. You'll see down in the corner it says Ooyala, and up there it says DataStax. About 2 weeks ago, I left Ooyala and joined DataStax. And my title there is Open Source Mechanic, which I've had a lot of really boring titles in my career. And systems administrator, senior systems administrator, site reliability engineer, tech lead. Those are all pretty boring. And I had the opportunity when I joined DataStax, and I asked, and I said, "Hey, can I have one of those cool titles that all the guys in Silicon Valley have?" And that's what I asked for, because it's kind of my background, it's kind of who I am and what we want this role to be with DataStax, which is kind of just going out, breaking Cassandra, finding open source projects, make them work with Cassandra, finding neat things to show people like you out in the community and working with the community to do really neat things with our technology. So that's kind of me. So what I'm going to be talking about is mostly things that I learned or pretty much entirely things I learned at Ooyala. I spent about 2 years administering Cassandra for them. We broke it in every possible imaginable way that we could come up with, and there was a lot. So we will tell you how not to manage Cassandra clusters, and how we made it better, how we got it better. And then what a heuristician, or what I call a heuristician, and it's basically an approach to performance tuning and optimization and troubleshooting that is different from being scientific about it. And you're all intelligent people and want to be scientists and want to be rigorous and be able to approach things and be able to be really confident you did it right. But sometimes when you're under the gun, you're in the heat of the battle trying to fix things, you don't have time for that, and you have to use this great ability that humans have, which is heuristics, and I'll talk more about that in a bit. And I'll talk a little bit about tools that I use for troubleshooting and performance tuning, some more settings, and then a few things about file systems like ZFS, BTRFS, and things like that we used and tested at Ooyala. So my role there was, I was tech lead of a team called Compute Data Services. We're basically rebuilding Ooyala's big data platform to be a platform as a service internally. It was a DevOps team. We had 2 systems administrators, a DBA, myself as tech lead, and I'm kind of more ops background, although I do a lot of coding, and 2 engineers. So there was that, and so we also called it Badass, which is a joke for us in English, and it's big data as a service. So we had about 200 Cassandra nodes. It's probably closer to 300 by now. Including now 114 node cluster that's in I think going into production in the next couple months. A little about Ooyala. I won't spend a lot of time on this stuff, I promise. They were founded in 2007. They have 230 employees. This is all the boring stuff. 200 million unique users in 110 countries, 1 billion videos played per month, 2 billion analytics events per day. What's important about that is when I talk about these systems that we maintain there, that basically all of those are wrapped around Cassandra, all of those analytic events ended up in Cassandra in one form or another. Sometimes they end up as aggregates. So in the new systems, it's all going in real time, all the events raw forever, or until they run out of disk. And so they've been using Cassandra since 0.4. When I joined, it was 0.6, and we went through the transition from 0.6 to 0.7 and 0.8, and I'll get to that in just a minute. Their clusters that they had when I started there, they stored analytics data, that's what about half of the Cassandra use cases. We also started using it as a highly available key store. We had a bunch of Redis instances all over the place, little applications. People would fire up their own in EC2. And we started going around and merging those into these Cassandra clusters so that we could get the high availability and get away from having these single nodes and wake people up in the middle of the night where they have to go and repair a node so that the Redis is available. And then we used it for playhead tracking, which is kind of, if you've used Netflix or other video services, you might be watching a video on your phone on the tube, and when you get halfway through it, your trip is over, you close your phone, you go home, and then maybe you start watching on your TV, and it should pick up in the same place. And so we use Cassandra for that. And there's a large machine learning system that they have that basically stores all of its intermediate data that's used for predictions inside Cassandra. So the original platform that they had before is way over there, there's the players. And these are basically all of you out in the world using services that might use Ooyala for their video platform. And what happens is their player sends pings back to their servers over HTTP. So it's a blob. It's got a whole bunch of information in it about where you are in the video, what video you're watching, what bit rate is it, how, what resolution is it at, a bunch of other stuff like that. That gets written to the loggers, which are basically just HTTP boxes that write to a log file. Those log files go into S3, where they're stored forever. And then every 5 minutes, there's a Hadoop job that runs, pulls those down into HDFS. And then another MapReduce job crunches those into Cassandra. And then there's finally a service that is used by the web UIs to read the analytics data and display it to our customers. This is a pretty Byzantine architecture or complicated architecture. So that's being replaced. So this was an 18-node Cassandra cluster. It's about an 80-node Hadoop cluster. Every 20 minutes or so, the Hadoop cluster would beat on that Cassandra cluster, push a whole bunch of data into it. I'll move on. Oh, no, that's right. Sorry. So the problem that we had here was the read, modify, write. This is less of a problem today than it was back 2 years ago, which was when you did this at large capacity, where the Hadoop cluster is basically going and reading a value out of Cassandra, and then adding another value to it, and then writing the whole thing back, and doing this 20,000 writes a second when it's writing, but it only writes for about 2 minutes. It gets to be pretty slow and really hammers on the database. You have to do a few things to make that work. So at the time, we're reading at read repair 100%. I think they're still doing that. And it has some problems in the storage engine. Now, like I said, with Cassandra 2.0, you have the compare and set, which would make this a lot cleaner. And they should definitely be looking at moving to that, but that's not my problem anymore. But here's the problem with it. And this is a really simplified version. And don't take this as canonical for how the Cassandra engine works, but it's a high-level view of how it works. So what you might do is say, we're going to go drinking. So this is my old team. And after the conference or the workshops. And so we've created a table, and these are our partition keys right here. And then these are just column values for each. So for each day, how many drinks people are going to have. So this would be the column key, the value, key, value. And so we're all good there, right? We can write that in. It's perfectly safe. We come along a few minutes later, or a day has passed, and then we decide we're going to update these values. I say, well, I don't think I'm really going to drink that much because I got to talk. And I find out that Phil is quit drinking for some reason, and he's not going to that night. So we have to update it. So we write that in. It goes in the mem table. This guy has already been flushed out to disk. This one has. So now we have some data in memory, some data on disk, and they're different. So when you do a read, it's going to go through the mem table first, and then if it hits in the mem table, you're good. It's going to return immediately, and if it misses, then it's going to go to SS table or go to disk. So we do it again. I decide, well, screw it. I'm going to drink a whole bunch. And did I just lose my mic? Yes. Sorry. So I write again. So we have the same thing again. If I read for me again, it's going to go, and it's going to get right out of memory. But now I have basically 3 values for the partition key, Albert, and these column keys. And what this is doing is creating a compaction problem. Is that you're going to have a lot of data that needs to be merged. And so at the time of size-tiered compaction, it was a big performance problem. And when you hear people talk about watching for your compactions backing up, this is kind of what's happening. So this is just important in terms of performance because when you get behind in compactions, you start doing a lot of I/O and you have problems with copying. I'm going to move on because but the other thing to keep in mind is if you can get to a point where what you're doing is you're writing over the values and you're just overwriting all the time the same values, it can work really fine. It's just when you read it back and you do that modify and write it back that you can get things where you can get into race conditions where you can read back an old value and all those things. All right, so we had that cluster up and running for a long time, and we got it all tuned up, and it's running just fine. I went off to work on another project, handed it off to some other people. They were working busy with a whole bunch of stuff, and the Cassandra cluster kind of got forgotten about. It was just sat there running. It was doing great for about 6 months, I think it was. And what happened is they forgot to run repairs for about that long, and all the tombstones had expired. They were past GC grace. And when we got to the end, we had this problem. We have all this data sitting on disk. It was about 25 terabytes worth that was no longer valid. We could be reading back invalid values because the tombstones were all expired. So what we decided to do is, this is pretty crazy. I don't recommend it. They took, basically one of our engineers pulled all the code out of Cassandra for reading SS tables and used some Scala code to basically write a map reduce that would stream over all of the SS tables and pull out the data and use custom business logic to figure out which values were valid, and then write out back into a new Cassandra cluster through the front end so that we had a completely consistent database at the end. It was a really ugly process. Took about 2 weeks to run. And so that's what we did there. What that did is it provided a lot of opportunity to make some changes in the database. And some of those that we did, that's on the next slide. We moved up to Cassandra 0.8 at the time. We were already at a 24 gig heap because the Bloom filters were so large. And at the time, I don't think it was tunable then. So that's definitely not recommended. I used to recommend that people ran larger than 8 gigabyte. Now you want to stick with 8 gigabyte heaps whenever you can, and only go larger if you really have a good need for it and you're not worried about GC latency problems. The other one is just a simple Sun Java update. Moved to Linux 2636, so we were on Ubuntu Lucid at the time, and I believe that was on 2632, and there were some features in 2636 we wanted to play with, and it turned out to be very stable. We were running that same kernel on other clusters in the environment and decided to merge it all to that. We moved to XFS on MD RAID 5, and there's a note about that, which is you can run JBOD or RAID 0. If you want to get maximum storage space, you can run RAID 0. If you like sleeping at night, you can run RAID 5 or RAID 10. And that's kind of important because the most important, or I'm sorry, the most likely component in a computer to fail is the hard drive. It has the most moving parts in it, and I've replaced so many hard drives and servers, I couldn't possibly give you a count. So when you're designing a cluster and you're building it from scratch and you're talking about whether to use RAID or not, even if you're just using software RAID, which is all I've ever used, definitely go with some kind of RAID. RAID 5 is generally will protect you through one disk failure. You don't need to go RAID 6 generally because you can always use Cassandra's replication to rebuild the node. But if you're running really deep nodes, a node rebuild can cost you an awful lot of time, an awful lot of network I/O, and latency because of the impact on your cluster. So I highly recommend that as a tuning for operations happiness setting. And the other thing is if you've seen me talking at other events here, always turn swap off if you possibly can. If you've got more than 16 gigs of RAM, turn swap off. If you really feel like you need to have swap on the system, or you've got systems administrators that in your company that own the machines and they insist on it, at least ask them to set this vm.swappiness value to 1 or some value very low, like 10. Because what that does is it tells Linux to not be stupid. What Linux will do by default, if you have swap enabled, is if it's doing a whole bunch of I/O across the file system, it'll actually start to evict applications to swap to make space for VFS cache. And that's great on desktop systems sometimes, like if you're running Google Chrome, then you kind of want it to do that because Chrome will eat up all your memory and you want to swap it out, get it out of the way so that you can have faster disk access. But generally, Linux's swap as default, configured by default, is wrong. And so the left-hand side, disable swap is the first thing you should try. And if all else fails, set VM swappiness to 1. And that would go in etsy sysctl.conf. If you Google it, there'll be instructions for how to set that. So we got out of that crisis and got everything back in shape, and then got right back in 6 months passed again, handed it all off. And we decided to move to a new cluster of hardware. And the same thing had happened again. It was just a human error, kind of just comedy of people not talking to each other. Anyway, so we already had the code to do this, so we did the same thing. And one of the tricks we played, it's actually a really handy trick to keep around, is GlusterFS is kind of a interesting piece of technology. People either love it or they hate it. The people who hate it have used it in production in large distributed setups, and they run into these replication problems and they swear it off forever. And if you talk to them, especially operations people, they will cuss and swear at you. But it has one mode where you can use it, and everybody agrees that this is pretty cool, is when you just do point-to-point mounts. So what we did is, when we were processing all these SS tables, the MapReduce job, is we exported all the file systems from Cassandra, where the SS tables were, to all of the nodes in the Hadoop cluster. So it was this big crisscross mount job from across all the nodes, so 80 to 18 in the first version. In this version, we actually used DSE MapReduce, so it was 18 to 18, so the GlusterFS mounts. Then we ran this MapReduce job that read it out of the database on the old cluster over GlusterFS, and then wrote back into the Cassandra on the same nodes that DSE was running on, and got us back out of that. We also made some other changes at the time. We moved to leveled compaction. We moved to DSE 3.0, obviously. The heap stayed really huge. I think that we actually fixed right before I left. The big mistake we made, though, was moving to MD RAID 0. So we said, well, we don't want to run into these storage problems again where we run out of space, so we're going to go MD RAID 0, get the maximum amount of space. It seemed like a good idea at the time. We hadn't had a lot of disk failures. So we did that. 3-4 weeks passed, disk failure. Node is down, which is fine. We go down, we put the disk back in, rebuild the node. 2 weeks later, another disk. These servers, they're new servers, and the disks start flaming out when most disks will flame out when the server is new or when it's 4 or 5 years old. You usually get a nice buffer in the middle where the disks just don't fail that often. It's in the first couple months, or it's way farther from now. So that's why I spent time on that earlier, is that you really, really, really want to be on RAID 10, RAID 5, or my personal favorite being ZFS with RAID 5 or its equivalent of RAID 5 or RAID 10. The other one is running on Ubuntu Lucid, and that's not something against Ubuntu. It's just that Ubuntu Lucid is older than Debian 6, and the DSE packages the C components are compiled on Debian 6, and it isn't compatible with the libc on Ubuntu Lucid. That probably doesn't matter to anybody today, but it's something to watch out for in the future. Just when you're loading up Cassandra, watch the logs, and sometimes you'll see that the native components don't load, and very often that's a libc linking error. And Ubuntu Precise works just fine. So, as I mentioned, we went to LCS. The other big change is the Bloom filter FP chance. I think that's changed a little bit recently. I'm still getting caught up on all this stuff. But the big change there is the default was 0.007, and that's why we were using almost 20 gigs or 16 gigs worth of heap for our Bloom filters. After moving up to 0.1, that dropped down to where we could go into an 8 gig heap. So we stayed with the really large heap for a while just to be safe on the safe side, and then we later moved to the smaller heap. This middle one here, the SS table size in megabytes, used to be a problem. The old default was 10 megabytes, and what happened when we loaded all this data in really fast through the MapReduce job was that we created something like 150,000 files on a single file system, and Linux gets really, really cranky when you do that, and when it's all in one directory. And I'd type ls, go to lunch, come back, and sometime after I got back to my desk, it would finish printing on my screen so that I could see what I was looking at. So just setting that at 256 megabytes, it's a pretty good size for Linux. The new default's 160 megabytes. That's also a really good size. With read-ahead enabled on the drives and the way modern drives are designed, you should be able to do really fast I/O, doing streaming I/O on 256 megs, reading and writing. We enabled snappy compression. That's now enabled by default in, I think, 2.0, and enabling it on even 1.0 or 1.1 was definitely a big win. And then this last one isn't generally recommended, but if you are running into compaction problems where your compaction is constantly getting behind but you find that your disks just aren't really that loaded. I tried things like putting that up to 500 megabytes, and I think that was a bug that was fixed. But what would happen is I put it 500 megabytes, and I'm still only doing like 10% of what my disk array can do. And by setting that to 0, it actually turns off that whole code path entirely, and your compactions will run at the full speed of your disks, and they generally keep up. And if you're on SSDs, it's definitely worth considering just to make sure that you don't get into a corner. So this year, the decision was made to rebuild this entire architecture, and we bought a whole new cage in the data center and built out all new hardware. It was HP servers, 8 drives, 128 gigs of RAM, 10 gig Ethernet out the back, really cool OSPF networking setup so that it had failover 20 gig. It's pretty neat. The lesson there isn't one. Sorry. This is starting to get old for me already. So things that are coming soon is this new cluster. The reason why we originally built it was what we wanted to do is change from this batch process where all these logs went into S3 and then eventually made their way into HDFS and then were processed by Hadoop. It's a very high latency process. At best, we were doing an hour, maybe 2 hours between when an event happened on somebody's device and when a customer could see the impact on their streams. The turnaround was far too long. So what we wanted to do is make those events write, because Cassandra can do this, we wanted to write them directly into Cassandra in full time. It's a project that we called the event store. And the idea is we'd get all the data into Cassandra and then start building the rollups on top of that so that we could do things like have really robust recovery. So this, go, thank you. Lag, there we go. So the new architecture, I'm sorry. Let's do this. So the new architecture truncates that process. The loggers are pretty much the same, except they write into a Kafka queue, which gives us just a little bit of a buffer. And then all that gets ingested directly into Cassandra. The ingest system is written in Scala. It's using Akka cluster. It's distributed out. I think it's a dozen nodes today. Eventually it's going to run on Mesos, so it'll be distributed across the whole cluster. And that's all running today. And then the really cool, neat thing that they had on top is they started using Spark. And if you look online, there's Evan Chan did a talk at Cassandra Summit in San Francisco, and the recording is online, talking about Spark, so I won't talk about Spark very much. We wrote a job server in front of it, which is this really neat pattern that I think most Hadoop and even sometimes in front of Cassandra and a lot of the big data services is a really good idea, which was Spark's interface is a lot like Hadoop's in that you got to know these environment variables, you got to know what port it's running on, you got to know which servers it's running on. It's kind of a real pain for the developers to iterate because they've got to have either a replication of the config in Vagrant or on their laptop or their own little mini cluster. What we wanted to do is get it to where they could write code for Spark, compile it into a monolithic jar, and just use an HTTP service to upload it and just get it running without having to touch any of the configuration goo. And so that's what the job server is. That's actually being contributed back to Spark and will be part of Spark in the future. And moving on. There was some other stuff on there. Hold on. Oh, yeah, that was it. Sorry. So the other thing we're doing is this block here. So previously, this was kind of, they wanted it to be secret how many nodes. It's 120 nodes. And what's running on there is, it's not just Cassandra. We're running Cassandra. We're running, Spark is running on the same nodes. We're running Apache Mesos. They're running KVM on those. So there's one KVM on every node. And so the idea was that old Hadoop cluster, the legacy one, is on really ancient hardware. And it needs to move. But the code is actually pretty dependent on the OS environment that it's living in. So we actually fired up KVM VMs across all of those with the exact same image on it so that we could hide the transition from all the Hadoop users without having to drag a legacy environment onto our hardware in the future. And so that worked out fairly well. And the real trick there to make this all work and tie it together is Linux has this facility called C groups, which is becoming a lot more well-known these days because there's a project called Docker that's getting really popular. But what that does is it's a little bit like the resource controls you used to find in Solaris or some of the other more advanced Unixes, where you can assign deterministic resource allocations to a specific process or set of processes. And you can do network or disk or memory, CPU, and you can do very fine-grained control of how many shares each container gets. So you can group processes together in the same C groups, or you can put every process into its own. But the point is the Linux scheduler isn't as stupid as it used to be. It used to be that every process was in the same pool, and it would use these heuristics to figure out what the prioritization was, and it inevitably, especially from a systems administrator's perspective, got it wrong. So C groups, definitely something worth looking at if you're managing large clusters. And then moving on to just kind of the art of performance tuning. Just to lead into that is there's a whole lot more to tuning than just making things really fast. And I've worked with a lot of different people who are into this and talked to a lot of people that are into performance tuning. And if your only goal is to make it fast, you end up having to leave a lot of things on the floor. If you want really fast access to your database, you turn off all the encryption, you turn off all the authentication. It's faster. You get faster connections because you don't have to do an authentication loop. Excuse me. And you don't have to deal with encryption overhead. But you do definitely need to think about it. Even if you're going to turn it off, you need to consider what are the ramifications of doing so. What is going to be the impact to my business of disabling security? You have really strong perimeter defense around your databases, it's probably not a big deal. If you're sitting in EC2 and you have all of your security groups wide open, it's probably not a good idea. So definitely make sure that you think about that. It should always be first and foremost. The cost of goods sold, or what is the impact on my business's bottom line? I can make anything fast if you give me enough money. I can go and give our sponsors, Fusion.io, I can go and give them $1 million for all the best hardware that they have to offer, and I don't have to think about this problem. Because I don't have to think about how to tune spindles and make them line up and do block alignment and all that BS. I can just throw hardware at the problem, vertical scale. For the next one is operations happiness. So in operations and developer happiness, but operations happiness is a lot of people. How many people in here are in operations? How many are in engineering? How many are in management? All right. So for the ops people, so if you're an engineer, and most of you are, just think about the fact that the operations guys, they're at the bottom of the hill, and bad things roll downhill, right? And they catch all of it at the end of the day. They carry the pagers that when you don't answer yours, theirs goes off and they have to get up and fix it. I did that job for a decade. If you design the system thinking about your operations people, they will love you for it. If you bring them in and talk to them and say, hey, would this make your life easier? Just asking the question. A lot of times, you're going to get a lot more cooperation. This is kind of the DevOps kind of culture change thing that a lot of people are talking about these days. But really, I mean, even with Cassandra, when I'm talking about use RAID 10, use RAID 5, ZFS, which is, obviously I'm a big fan. You know, these things make the operations life a lot easier, actually, at the end of the day, because it makes managing the system, when failures happen, you can look at, the pager will still go off. But I used to do this all the time, where a Cassandra node would throw me a page, I'd roll over in bed, and I'd look at my phone. Oh, that's a Cassandra node, right? Because I just didn't have to get up. It wasn't an emergency. I've got 3 replicas. So that's a big thing to think about. Obviously, developer happiness for yourselves. But I also encourage operations people when I talk to them to do the same thing and think about, well, sure, you could make this the most secure, awesome, fast system ever, but your engineers are going to have to write all this extra code and deal with all this extra deployment bullshit. And they don't want to do it. So you really have to balance all these different things. Obviously, the physical capacity, reliability and resilience kind of feed back into cost of goods sold. What is your business trying to do? How many nines do you need to have? And then ultimately, all these things are about compromise. So as I mentioned about the heuristician thing, or heuristics, as I've described, we had all these emergencies going on at Ooyala where things were on fire and the business is running at full speed. We don't have time to sit down and go, well, I could take this new cluster and go and run, lay out all my tests in a spreadsheet. I'm going to do 8 gig heaps and 12 gig heaps and 24 gig heaps and run a test for 24 hours on each one. And I'll run Cassandra stress and YSDB or whatever that one's called. And really just kind of make sure I got all the data and go and just put together nice graphs and display it. You can do that stuff, right? You can write a nice paper about performance tuning. But that takes a lot of time and a lot of resources. And very often you just don't have access to it. If you need to have a performance lab, if you've got a 1,000 node Cassandra cluster in production, you're not going to have a 1,000 node lab. So at some point you really do have to do some extrapolation. You do need to kind of guess, make educated guesses at what you're going to do. So that's what I mean about, I would really love to be scientific about these things. I hope I someday will have the time to sit down and actually do the rigorous kind of study and make sure that my data is clean, but that's probably not going to happen. So the thing is the human brain is really awesome at heuristics. It's what we do it better than pretty much any other creature, literally, actually. Maybe dolphins, right? They seem a lot happier than us. So the idea is that you need to lean into that ability. You need to trust yourself, trust your judgment. And there's a book by Malcolm Gladwell, who's this guy right here, called Blink. And I'm pretty sure it's translated into a lot of different languages. I tried to check, and I couldn't find a good reference for it. But it's a really good kind of pop overview of the science of making educated guesses and making really fast snap decisions. And it turns out that people are a lot more accurate than they think they are in terms of your first judgment is usually a lot better than your second guess. And then kind of the approach is to make these changes really kind of incremental small changes and just keep building up knowledge in production. Because production is the only place where you're going to know what's going to happen in production. Because a lot of times, even your test lab, unless you have lots and lots and lots of resources to throw at it, and it's going to cost lots of money, that 1,000 node cluster again, right? You got $1 million worth of hardware sitting there. Nobody's going to sign the check for you to put one in a lab. You make these changes in production, you observe them, and if it's really dangerous, you try to test it somewhere else. But at the end of the day, you got to do the same thing in production. And my contention, or what I'm proposing is that Cassandra is a really great place to kind of practice this because you've got replicas, you've got a large ring, you've got some slack to make mistakes and correct them. So I do this a lot, and I did this a lot at Ooyala because I like shiny things. I really like new technology. I'm always running the latest kernel on my machine at home. I've got VMs on this laptop that are running crazy stuff. So, I really love running the latest Linux kernel. There's always some new feature that's really interesting. Huge pages, transparent huge pages, which are actually a boon for things like Cassandra and any Java application. ZFS on Linux. I've been playing with that for a few years now. It's finally made it to where it's stable where people can start testing it in production. BTRFS is kind of the little brother or wannabe of ZFS. It's a nice little file system. It's got a lot of similar features, copy on write snapshots. And really, it's the transparent compression that was really interesting for us with Cassandra. Prior to Snappy and even after Snappy, because it's LZO compression, and it compresses everything instead of just the data that's pushed through Snappy and Cassandra. We played around with a lot of different JVM parameters, and almost all of this stuff was tested in production on production machines. What I would do is, or some of my colleagues would do, we'd just pick a node or two distributed throughout the ring, and we would test on those. So if I was saying I want to do a kernel upgrade, I want to go from 2.6.36, and I want to go up, new Linux 3.0 kernel is really awesome looking, right? It's got that shiny big 3 at the front. I want to do that. I'll pick this part of the ring, or this node, and I'll test it there. And if I want to test it on 2 nodes, I'm not going to put it on this one, right? So it's really simple with Cassandra because you have the ring there. It's really easy to visualize. Put your kernel upgrade here and put it over there. If you want to be conservative, do the same thing with your operating system upgrades. I mean, start doing your operating system upgrades if you're not doing them, within minor releases. If you're running an LTS, RHEL 6, or Ubuntu Precise, you need to be doing those upgrades for the security patches or very often performance fixes. And a lot of people don't do them because it's dangerous, right? Everybody's been bitten by it. The systems administrator went in and did an apt-get upgrade, and then you come in the next day and none of your crap works because something changed in the libc. So with Cassandra, you just change it on 2 nodes, let it run for a week, 2 weeks, a month, whatever you like, and then you come back to it and you do it on the rest of the nodes. Or maybe you just do 1 node a week. But that's up to you, but what I'm saying is you can run these experiments. And this is exactly what we did. Moving on to tools. This chart I did not make. Brendan Gregg is an engineer at Joyent. He came from Sun, is I think the author of dtrace. If he's not the author, he's definitely the expert. He's got a lot of really cool slides out there. He does a lot of talking at conferences. But this is one of my favorites. The links here, the slides will be up, and there are older copies of this talk out online if you want to find them, if you want to grab this link. So what I'm going to talk about mostly is dstat is probably my very favorite Linux tool that a lot of people haven't heard of for observing performance metrics. But this chart, I would print this out and keep it at your desk. Anytime you're working on a Linux system and you think something's happening with the CPU, you can look up here and you can see there are a few different tools that maybe you haven't used before that you can use. PIDstat has some really neat stuff for watching what states your processes are in. And that's enough on that. So this is what dstat looks like. And it's not scaling very well, but yeah, I'll kind of walk you through it. So the command that I type by default when somebody says that this system is doing something funny. So my approach, being a systems guy, is I log into the system and I run dstat minus lrvn10. And what it gives me is, over here is the load average, and then we've got processes. This is all my memory, so this free memory, in-use memory, buffer cache, and total memory. Swap, which is always 0 if you're doing it right. I/O, context switches. So it's got all the stuff that VMstat has in and more, and it's color-coded too. So if you're not colorblind, you can watch this flow by and you'll see things turn red and yellow when things are going wrong. And very often when you have a node that's, say, under compaction problems, right, it's backed up, you'll see the disk I/O, you'll instantly see it. The disk I/O will be red and it'll be going at 300 megabytes a second or whatever. And you'll have one processor peg. This will be, the idle will be at like 25% and you'll be at 75% idle. And I/O waits some insane number. So it's a really nice tool just to leave running in terminals. What I'll do is I'll fire up on my Cassandra clusters, I'll fire up screen and fire it up on all the nodes in the cluster and just leave it go, and sometimes for weeks, so that when something goes wrong, I can just flip over to the window and I'll see this. I'll see the history going back for the last few minutes. And that's really handy when something's already happened and you want to look back through history. It's not as nice as having a good monitoring system, but it's really good for kind of just point in time checking things out. This one is a tool I wrote a long time ago, and I just kind of drag it around with me because it's really handy. It's out on GitHub. I haven't seen any other tools like this. What it does is it SSHs into all the boxes in your cluster. So you have a 25 node Cassandra cluster. It'll connect to all of them and keep a persistent connection open, and then it reads the stat files from proc on Linux and calculates these values every 2 seconds. So this whole thing will update, and what you can do is watch the state of the whole cluster, and you'll see disk I/O moving around the cluster. This is disk I/O here. This is network I/O. So you can see the behavior of the cluster in a holistic view just right in your terminal. There's no web browser, fancy stuff. And then these are just aggregates down at the bottom. IOStat, I hardly ever use IOStat. But I use this one command of it, which is iostat minus x1. And what this is really handy for is if you have an MD RAID device or any kind of disk aggregation system, so it'll work with ZFS or MD RAID or device mapper. What you're looking for here are these columns here, and you're looking for outliers. What usually happens with a RAID array is you have one disk that starts going bad and starts dragging down. And so when you have stripes going across a RAID set, it's going to hit that disk and it's going to spike latency and slow the whole I/O down for the application. And a lot of times when you're looking at the database and you're scratching your head and what the hell is wrong with this database? Everything looks fine. Why is it slow? It's probably hidden behind the RAID layer, and that's why your I/O is really slow. HTOP is one that I'm surprised that more people don't use. It's an improved top, so everybody uses top to figure out which processors are in CPU. The nice thing with HTOP is it shows you all the threads by default. The normal top can do that if you hit capital H, but this one's really nice. You can turn on color coding, you can configure it to do all kinds of crazy stuff, and it gives you this really nice processor bar where you can see what how busy all your processors are. And it's color coded as well, which is just kind of nice. I like shiny things. This is the workhorse of Java, right, is jconsole. If you're running Cassandra, you probably used it. Basically, all the good stuff you want to get to in terms of really screwing up your cluster are available over GMX. I recommend if you're administering clusters that you just flip through the tree every once in a while and look at the value, especially during version upgrades, and look at what some of those values are, because there are some of the hidden things in there, like there's the assassinate node or whatever it's called for getting rid of stale nodes. A lot of the kind of real nuts and bolts stuff that my colleagues at DataStax will come in and help with are kind of hidden in there. They're not hidden, they're not easily found. So, I mean, make sure you know how to connect with jconsole, make sure that the firewall rules are set up, because what I found is a lot of times people have these Java applications running in EC2 or whatever, none of the ports are up for JMX, a lot of times it's not even enabled. So just make sure that it's on any Java app. And this view right here is, I think this is par Eden. So this is where you can look and make sure that your new size is set correctly. That's a pretty common problem with Cassandra, is that the new size is too small and you end up with these kind of nice jagged patterns. I'm not the best person to talk about that, but I have used this quite a bit to find those problems. I'm going to speed up a little bit. Opscenter is really cool. This is what a 114 node cluster looks like, and I just love this view. We loved having it up on the dashboards at work where people would walk by and gawk at it. Obviously, nodetool ring can show you some, everybody knows that one. CF stats, and there are a whole bunch of neat other commands under nodetool you should familiarize yourself with. The big ones to watch here are the SS table count, which is the one I ran into. If that gets up into the hundreds of thousands, you're going to have a bad day. And the Bloom filter false positive ratio, if that's constantly at 0, you want to consider adjusting that value up so that you get some false positives, because otherwise you're just wasting memory. Come on. Proxy histograms. I'm going to move over these. I'm getting the big time sign. Obviously, when you spin up a new cluster, the first thing you should do is try to put some stress on it. Not just to benchmark it, but also to make sure that the hardware is burned in, because as I mentioned before, hard drives like to fail when they're new. They fail when they're new, and they fail when they're really old. So making sure you do a whole bunch of I/O on new drives, you can shake that out before you go to production. Cassandra stress, obviously, there's been a lot of work being done on that these days to make it a little easier to use. YCSB, a lot of people use that. Test in production, watch your production traffic. That's why I spend a lot of time on system stats, is because in production you can always log into systems and without causing problems be watching system stats and be able to look. And if you get good at watching the systems, you can see traffic. Maybe you look at your monitoring system and see your website traffic or whatever your application is, and start to correlate that with what's happening on the systems in Cassandra, and then you get better and better over time at detecting issues before they become a problem. And a lot of times I end up just doing homegrown tools, just because I like to just turn on all the load all at once and see if I can break it. And that's also a very good test that most existing stress test tools won't do for you. Am I out of time? No, I have 2 more minutes. So these will be available in slides. This is the syscontrol comp that I mentioned earlier. The first one is totally unnecessary, but I love it, especially on MapReduce systems that burn through PIDs like crazy. It sets the PID max to 1,000,000. So instead of the PID rolling over at 32,000, it will actually go all the way up to 1,000,000, which means that it doesn't cycle all the time. So when you type PSEF, you don't see, your processes aren't constantly mixed all over the place. You actually get a nice period of time where they're nice and linear. It's nice for observing systems. The rest of these, I'm gonna have to skip over. The bottom two, I don't really recommend as much anymore, but they can be pretty important for I/O systems. And definitely these network settings on every Cassandra box should have these. It basically makes sure that you open up the throttle on network. And I'll skip that. If you have dual socket Intel systems or AMD systems, modern ones, actually I'm out of time, I'm sorry. I can talk about these later. But make sure that you consider NUMA issues when you're having problems with memory bandwidth. It happens, I've seen it in production. Java has support for NUMA, or the NUMA control interleave will actually make sure that just flatten it all out and it treats all memory as equal and will spread the load across all the nodes automatically. So sorry I didn't get to cover those slides, but conclusions, tuning is a multidimensional effort. You need to look at a whole bunch of different considerations. You look at security, look at systems metrics, look at database metrics, look at application metrics, and talk to your operations people, talk to your engineers, work together to find the right balance of things, because just tuning for pure speed is almost never the right answer. And production is your most important benchmark. Thank you very much.